guys, Cyprien here from FE for All, and in this video we'll have a look at how to simulate this wrench into Salome Meca with Code Aster, and I'll be using Aster Study to do this. And this video, I'll really go into the details at how to get this kind of very nice mesh, how to get some kind of transparency, how to animate all of this, how to apply a lot of filters in Paravis to extract the right mesh stress distribution. All of this stuff, I'll go into it into this video. So watch the video and let me know what you think at the end. And if you like what I'm doing, please give it a like and subscribe to my channel. And let me know if you have any comments. If something doesn't work for you, if you have questions while you're watching this video, please leave a comment on the video or on the blog. Let me know. And if I know the answer, I'll reply to you. So let's start. So I just opened a new window of Salome Meca 8.3. So I'm using the 8.3 version. And there are some new versions released right now, I think, but I found out this one was a bit more stable and less errors. So in case you get some errors with the latest version, you can switch back to this one. And I'm using the Windows version. So the Windows version isn't officially supported by the team who is developing this Salome Meca, but it works rather well for simple static study. So that's what I'll use. So let's start by creating a new document and opening the geom module in which I will load my CAD file. So let's go into the file and let's import my step file. So I will have a dialog box telling me that there is a millimeter unit which is embedded into the file, and I can choose to ignore it or not. So it looks like it's not very important, but it's actually pretty important because based on if you choose yes, the model will arrive in millimeter unit, but if you no, it will be loaded in meter unit, so your model will be like 1,000 times bigger. So I'll choose yes. And you see the model is very small here because it's in millimeter unit. You can zoom like that. And I'll make sure that I chose the right choice. Never trust like that the model, because if you just look at the dimension here, you don't really know. And sometimes you go over the whole analysis and you realize that the final result is wrong. You don't know why. And that's probably because of something like that. So let's go into inspection, and there is a dimension bounding box feature that I can use to basically draw a bounding box around the model. And we see that the x-axis is comprised between 0.17 and 0.02. And because I will use meter unit to be in SI unit when I do that. So if I think that I am now in meter unit, this is 0.17 meter, which is 117 millimeter, which is fine. It's exactly what I want. So I'm okay. I'll just close that. So now I have to prepare for the next step. I have to think about what kind of boundary condition I'll be assigning to this. So right now I extract the right surface groups that will be used to extract the mesh groups and to compute. So what I'll do is that I will fix those two faces here and here, and I will apply a pressure on those two faces here. So I need basically to extract that. So I'll go into new entity, group, create group, and now I just have to select the right faces. So one face here, then let's select, okay, I just selected one. Make sure you select the right faces. Okay, so this will be the fixed faces. Apply. I don't know why sometimes the camera is slightly difficult to. Anyway, and by the way, if you don't know what I'm doing to rotate that, as I press Control on my keyboard, and if I press the center button of my mouse with Control pressed out, I'll be able to pan like that. And if I press Control plus the right button of the mouse, I'll be able to rotate the model like this. So that's easy way to use this. Anyway, okay, let's choose those two phases here. So sometimes the faces can be selected. So I found out that you have to rotate the model like that. And I press Shift to select two faces at the same time. Okay, I got two faces, and those will be pressure surface. So we can call it pressure surf like that. Okay, so let's just check that I selected the right faces. You see by default, when I selected the groups, everything else gets hidden in the walk tree. So you can reactivate that. So and just making sure that I have selected the right faces, which seems to be good. Okay, so now I'm okay with the geometry. This wasn't very complex because the CAD is already ready, right? Okay, so now I can go into the mesh step. So let's go into the mesh and let's create a mesh set for that. So go into create a mesh set. And the simple, I'll just use the simpler option for this, because when the CAD is not very proper to make a hexagon or this type of special mesh, then I'll just use this one. That NetGen 1D, 2D, 3D. This will be almost automatic. Nothing, you won't have to set up 2D, 1D, etc. So, and then I have to assign some parameters, and I'll show you a bit later in the video how to refine the size of the mesh. For the moment, I'll just go with the standard mesh just to see what I get. Compute. So I don't see it right now, probably because it's very small, that's why. So there's probably a button here somewhere to resize, I think. This one, reset, yeah. This resets to the standard view. Anyway, you can zoom like that. So, so this mesh is really coarse in some areas and fine in some others. I might have to refine it right now because you see here, this is first order elements, so it doesn't even follow the curve like that. So let me show you the difference between first order and second order. Second order, so you can like that open the mesh and the hypothesis that you apply to it are assigned in red. So you can edit and you will be able to change some of the stuff here. So if I use second order right now and I change this, you see you still have some nodes. So sometimes you don't want that. So I'll just also right click and clear the mesh data totally. And then I just remesh. So mesh, here, mesh compute, right? Let's see if I get something better. So we can see it's already better, right? It's already, it goes along the curvature because this time it's the same size, but I have second order mesh, which means that I have a node in the middle here. So we see very clearly that those triangles are not more just one surface, they are some middle nodes here. So let's refine a bit more, just a bit more for this first try. Because and here I have a max size and a min size. So I found out that if you change the fineness like that, it doesn't really have any impact on this as long as those values are set up. So what you have to do is, for example, let's choose, here I have 0.02, you can say. So let's choose 0.01 instead. And let's keep this for the minimum size. And let's see if that's enough. Let's clear mesh data and remesh. That's slightly better, but not that bad. Not that better, because in those areas you still have one element in the thickness and all that. But for a first model, I'll just go with that, and then I'll refine later. So that will be a good point to show you how, once you generate the model, once you did everything, how you can come back to your mesh to refine the mesh, and without having to change all your study. Okay, so once I'm good with all of that, I will generate the mesh groups. So I have those two geometry groups here. I need to get the same, but for the mesh, because what the Code Aster solver reads is ultimately the mesh groups, not the geometry groups. And you can go into the mesh, and there is a very useful function called create groups from geometry. This will allow you to select directly your geometry groups like this. You press the little arrow here, and this will appear here. Apply, and they will be created. Let's have a look. They are hidden by default. So if you activate them, you see that they appear in a different color, which allows to really see what are those mesh groups. And now I'm okay with that. Well, I'm not really okay, because those mesh are really huge, and I probably won't get good results. But that's for the first try. Always take something a bit coarse, because it will be faster to compute and to correct your mistakes. If you take something very, very small from the beginning, and every time you try to iterate to correct your model, it takes a lot of time to calculate, and then basically you lose a lot of time for nothing. If your model is coarse, you can easily debug it. Okay, so that's the mesh is done. So because I will use Aster Study, I don't need to export the mesh. I can directly read it from Aster Study. But in case you would like to use Code Aster Solver without Aster Study, you could just export your mesh like that. There is a function export into a MET file, for example, and then read it again. So you'd have a separate mesh file. I don't need to do that for this analysis, because I will be able to read it directly from the Aster Study case. Okay, so now let's switch to Aster Study. Let's choose the stable version. Now let's go and create a new stage for this simulation. And in this stage, now that the stage is added, all those options will be available for you. And basically, to create this simulation, I have to go in a certain order. And it's more or less, for static analysis, more or less always the same thing. So if you understand this process, you just have to do the same. So the first step is always to read the mesh. So the name of the command and in the menu are a bit squeezed, so it's difficult to see what is written. But you can, like that, click. You can leave the mouse a certain moment on the command, and you'll see the full name of the command. So the first command is always almost read a mesh. So in this command, you just have to select your mesh. So if your mesh is in the SMesh module, like I did, it will appear like that in the drop-down menu. So you just have to click on the drop-down, and if this is an external mesh that you have from another software, or maybe you already exported it to MET file, then you'll have to click on the three dots and find your file in your computer. Okay, so now you see my mesh is imported, so everything is fine. I don't see the mesh groups, but the mesh groups will be imported at the same time. So that should be fine. Next step is to, it can be to assign a finite element model, or it can be to create the material. So I'd like to create the material first, and it starts with define a material. So I have to first to create a certain material. So I just use a steel material. And you have to choose a type of model for the material. So you see you have a lot of models available, but most of them are for nonlinear material. The simplest one is just linear isotropic elastic. So just click on that. Then you have to input the Young's modulus and the Poisson's ratio. And one of the frequent, let's say, mistake, and I think I'm myself, let's say, guilty of this mistake in some of my previous video, is the unit used here in the Young's modulus and the Poisson's ratio. So make sure that if you are working in meta unit, Young's modulus should be in SI unit, so in Pascal, not in megapascal or in gigapascal. It should be in Pascal. So in this case, I'll use 2 and power 11 as the value for the Young's modulus and 0.29 for the Poisson's ratio. Because I don't have gravity in this, I don't need to input the density. So just use that. Okay. Okay. Done for my material. Now let's go into assigning the material. So now that I have defined it, I need to assign it to my, so you have two ways. You can assign it to the mesh or assign it to the model. I didn't create the model yet. I have only the mesh. And by the way, how do you know which kind of object you already have? Just look into this, this data settings view. You see, this is the name of the object. So I have a mesh object right now and I have a seal object. So I have those two objects. And because I have the mesh object, I can assign to this. If I have a model, I will have right after, I could assign it to it. It's more or less the same, but it depends if you have several parts. For example, you have several mesh, then it might be easier to assign to the whole model. And now I have to say basically everywhere in my model, I'll use this steel material that I've created. Okay. You see that when your command is not fully defined, it will appear in red, but when you have all the options for it, it will be displayed in black. So it's fine. And here in this window information, you have the actual Code Aster syntax way to write this as a command. So I'll show you maybe later how to export the command file in order to have a look at what Code Aster is really using as an input. For the moment, just let's focus on data settings. So I have my material assigned. I have my mesh. Next step is to assign a finite element model. Let's go into finite element. And let's create one new model. Everywhere. And I have the choice between acoustic, mechanical, thermic. This is a mechanical simulation. And you see I have also several types of modelization. So this will be 3D. So it's the easiest actually because I don't have to define anything more. If I was if I were to choose, I don't know, 2D, this T or something, I would need other kind of comments afterwards to complement the model. In case of a 3D, it's pretty straightforward. You just need choose 3D and that's all. Okay, so now you see that the model is defined, and when it's defined, it's actually automatically placed before my material. So the order of the comments, it's automatically resetting. So we could argue that it would probably be best to generate this model first, right after reading the mesh, but actually it doesn't matter. You can define the material or the model. Okay, now that this is done, I have to assign the boundary conditions and the loads. So I go into this window. So again, a lot of stuff here, a lot of strange names. The one which has to be used is this one, assign mechanical load. So make sure you use this one, because if you look at that, it looks the same, right? But this one is for thermal, this one is for variable thermal load, so this one is actually for mechanical. And now let's assign this to my model. So I can assign several loads within one unique load object, which is interesting. So, and these are all the types of loadings which are available. And maybe one of the most useful is this, enforce degree of freedom. This will allow you to fix some degrees of freedom. So I create one like that. So the first thing is to choose a group of elements on which I want to fix. And that's where the groups of elements are actually useful. And I'll use, so I could just go for activate that, all the 6 degrees of freedom, or actually just 3, because 3D elements only have 3 degrees of freedom, and I could just say, okay, this is 0, 0, 0, it's fixed. But another way to do that is just to activate this liaison encastrée, which means basically that all the degrees of freedom are fixed. So this is a way to fix all the degrees of freedom. So liaison in French means link, and encastré means fixed. So it's a fixed link, right? Okay. Now let's go on to this phase here. And I want to assign pressure. So I can use this small bar to search for press. And I see that I have several types of pressure load. So I have pressure from results, not this one, pressure sigma, pressure rep, pressure epsilon. So you need to go to dive into the documentation to see what those actually do. Or I think you can actually use this maybe to kind of documentation. It doesn't always work. Sometimes it just indicates what, maybe this works on the Linux version. On Windows version doesn't work very well. Maybe that's possible. Usually you click here and this will tell you what it is, but I guess it's only working on the Linux version. There are some features which are only on Linux because, as I was telling you before, the Windows version is not officially supported. So it's basically a small company who decided to make the port of this version for all the engineers who want to use it on Windows. Okay, anyway, the one I want to use is this, pressure rep. So why a rep? It's rep like répartition, I think, which means distribution in French. So it's like pressure distribution. And this will allow me to choose for some surfaces, this one, and give a certain value for this, and this will assign a certain pressure to this. So don't forget the value I'm doing should be in Pascal. So I think should be in Pascal per meter, something. Oh no, this is a pressure value. Anyway, let's choose this value. Okay. So if you want really to be sure about the value of the load and what value this will be used, check the documentation and have a look at the difference between the different type of loads. Okay, so the loads is assigned. Now I'm ready to assign my analysis case. So Code Aster supports several types of study, and actually quite a lot. It has dynamic, it has static, it has model and thermics. So this is static, so you have to go into the small static, and this should be this one, static mechanical analysis, Meca static. Okay, now let's select the material field. Let's select the model. Let's select the loads. So here it is. So you have some option if you want to multiply the loads by some function or this kind of stuff. I don't need that. Or if you have several loads, you can add several loads like this. And this is all you need for this. And what really this Meca analysis is doing is that it's basically taking the different inputs objects that you created before and it regrouped them in one place. So click on here. This is done. Now one thing that this will always be a problem for beginners, so take care about this step, is by default the analysis only calculate the displacements at the nodes. So if you want to have additional type of results like stresses on elements, stresses on nodes, von Mises stresses, this kind of thing, you have to add a post-processing command called Calcul, which will basically tell this analysis that, okay, I want more results than just the displacements. And here, make sure in the name, use the same name than the analysis. So you could just use this. I think they have reused the input object. So if I check that, it will automatically, I think, select this. Or I can just write manually the name. So it should be the same than your analysis object. And now I can choose what type of additional results I want. So if I go into contrainte, which means stress in French, I can add some kind of stresses. And here again, those notation can seem very strange, and what you have to understand what they mean. So first of all, you have EFGE, you have SEF, you have sigma, you have others. I don't know myself what they all mean. I just know that this one, SIF, is pretty useful. And what it means is that I think C means sigma, so it's the name of the stress. In French is generally noted as the sigma, the stress tensor. And the F means, I think, efficient or efficace in French, so sigma efficient. And you have three types of results every time. You have ELGA, ELNO, and NE. So ELGA means element ghost point. So this will give you sigma efficient at the element ghost points type of results. This will give you element node results, and this will give you the nodal results. So one important thing to know is that if you only want the nodal result, you cannot just select this. You have to have three types of results. You have to have the element ghost point, you have to have the element node, and you have the element, the SIF node. So if you have the three like this one will be calculated. If you only put this one and you don't put those two, this will not be calculated, because this type of result basically take the results from those two and do some post-processing to obtain those results. So that's important to know. So that will give me the stress results. Now, deformation means strain, so we'll get the strain. I have the energy, and critère, so criterion. It's basically von Mises and other type of stresses, like can be Tresca and all of this. This will be calculated here. And here again, I have psi EQ, which goes for sigma equivalent, I guess. And I'll put sigma equivalent ghost points, element node, and node, right? Okay, I have those 6 type of results. I'm okay to continue. Okay, so now I'm already almost done. I'll still have one step, which is to actually print out the result. Because now I'm calculating everything, but I have no output. So I need to print those results to a file. And there is a last command into the output, which is imp Rusu, which set the output results. And here I have to choose the format. So I'll use med format, which is the format of the results that will allow me to read the result within Salome Meca, within the paravis. And I'll just create a file for this. So I'll create a file called range2.armed. Armed will be the extension of the results. Click on save. And now I'm ready to compute. So to calculate the results, you have to switch and go into the history view. So there's a tab here. It's a bit difficult to see, but this is actually important. There's a case view and there's the history view. That's how you switch to the actual solver running interface. And you have the current case, which is whatever you created already. So if you already run some simulation, you'll see some cases which are already below that. Now I didn't, so I have click here to add this stage, and there's a button called run here. Okay, I didn't save my study, very bad practice. So let's save it under the name you want. And now you can run that. So you see in this window the message file, which will basically indicate you what is going on. So the solver will go through all the commands into your command file, and it will tell you if something went wrong or if it calculated. So if you see something red like that, it means that you have a problem somewhere in your model and it wasn't able to calculate. So then you go down until the end and you just look at what is actually the problem here. So okay, so here it tells me that the field cif-elga is already present in the data structure at all required times. So I won't need this. So I put it 2 times, cif-elga, cif-elno, cif-ne. So it's, yeah, maybe I don't need to put it 2 times. But that's just a warning. Let's go and change this just to see if this was the problem. Okay, I also know that I forgot something. In the set output results, I forgot to actually, so I set up the result like this, and I forgot to add the results to this. So it's a classical mistake actually. So you'll probably do the same. So make sure that you activate results here. Otherwise, I'm not printing anything to the output file, right? And I have to give it the result from this wrestling. So maybe that was why I'm getting red, because I think it's calculated, but it's not outputting anything. So maybe that's why it's red. So let's click on current case and let's run that again and see if this time it becomes green. Okay, that time it's green. So that was probably the problem. So you see that you probably get the same mistake. So that's actually good that I made this mistake. Good. I'm showing you some of the stuff you have to be careful about. So now we're ready to look at the results. So let's go back into the case view. And to look at the results, I have to open them into Paravis. So I could open Paravis and try to find where my results file actually are into my files, or I can go here in my tab data file. This is the files which are linked to my study, and this is the result file. So if you right click on this, you have open in Paravis, and this will automatically open the Paravis module and load this file. Okay, good. So now I have opened my geometry. Let's have a look at the properties which are within this file. So you see that here in this this property editor, you can see all the kind of results which are saved into your file. So in case you don't have anything here and you're wondering why I don't have any results, then you'll have to look here and see if those results are actually present here. If they are not, that's probably because you forgot to assign the result to your set output results comment, like I just did. But I added them back, and now it's calculated. So let's have a look now. Let's have a look. So now the other thing which is strange is that here you have 1, 2, 3, 4, 5 type of results, but here you only see 3. You only see displacement and the von Mises. Because by default you only see the nodal type of results, you have to apply a filter to see the other types. So let's have a look at the displacements first. So that's the displacement. You have different ways to view that. If you want to view the elements, you can activate this. This is the magnitude of the displacement. You can view also each individual displacement direction, dx, dy, or dz. Let's have a look at the von Mises stress on the nodes. And I'll just hide the mesh surface. And same, you have magnitude, and here you have von Mises stress cap, principal stress, and a lot more. Let's look at von Mises, and that's basically what I'm getting as a first approximation. So of course, this mesh is very coarse, so I would not think that this is the right solution. This is probably not that great, because calculating of stress requires small meshes, much smaller mesh than the displacements. So generally, even with such a coarse mesh, your displacement might be accurate, but your stress will probably not be. And especially if you look at this area here, that's a bit strange here. You know, I fixed that, and I don't know what is this, why I have something like that around this. So now let me show you how to get the displacement deformation shape, because this is also something you need to know. How do you get the deformed shape? Because now you want to see how that's actually deformed, right? You only see the colors right now. Well, for that you have to apply filter. So there are some filters here in Paravis, and the first thing you have to do is to go into here, the properties, and there is a function called generate vectors. So you have to activate that and apply to so that the displacement will actually be a 3D vector. And then you can apply a filter. So don't forget this intermediate step to apply the generate vectors. Otherwise, you don't have a vector. And then you have to go into common, warp by vector, apply that. And now you're able to see this, this animation here. Well, it's not animation, it's just deformation. So you can view the initial shape here, and both are in the same. So what I can do is actually put some opacity a bit in this layer here. Opacity. It's a bit better like this. And you can control this intensity of this displacement using the scale factor here. So you can just apply this. By the way, if you wanted to change like that without having to apply that on the button, you can activate this option. Apply change to parameter. So when you move the cursor, it will automatically like that. So that for small models, it's okay. If you have very big models with data, don't do this. Okay, and if you want an animation, go into the View, Windows, Animation View, and go into, now I have to add my, let's say, warp by vector and scalar factor here. Click on the plus, and I'll be able to, like that, scale displacement. And this is the animation, so you can put like that. Cool. So now you know already the basics, but for this video, I'd like to go a bit further than that. So I'll show you a bit more advanced stuff, and for example, how you can refine the mesh and how you can understand the results out of this. Is it correct? Am I reading correctly the results? These kind of things I'd like to show you also. But before we do that, I'll still have one thing to show you here. Is I told you that I cannot see, basically, I can see only the nodal results. I cannot see those ones. So if I want to see all the results, I have to apply a filter to this, which will be the mechanics, and for example, LNO to surface. Apply. I'll just hide this. And now I'll be able to see all the other LNO field. Now this is the element-wise type of results. You see very well that this time the distribution of stress is going along the elements and not along the nodes, because you have some discontinuity in between the elements. So yeah, I can display the elements like that. Maybe it looks better. See, and this is how stress is actually calculated in this model, because stress is always calculated on element surface. It's an elemental type of value. It's not a nodal value. So whenever you get a nodal distribution of stresses, it's always an approximation. There is a averaging of stress at the nodal. And what is basically done is that if it's wrong here, you won't see it in the averaged results. So you might think this is correct results, but actually sometimes it's better to look at the elemental value. Okay, so now let's have a quick think about how to refine this mesh, because I don't like it very much. It really doesn't give me very good results. So let's go back to my meshing module, and let's have a look at how to remesh. So the geometry won't change, and the mesh group will probably change. So I'll just delete the mesh groups. That. And now to remesh and refine, I'll just go and clear the mesh data and just edit the hypothesis. And now it all depends how much you put into those values. So we have to basically do some try and error to see what will be good. So if I try a 0.5, and let's keep the minimum size like this for the moment. Let's try to remesh that and see if this gives me kind of better. Okay, so it seems to be a bit finer here, but still not exactly what I want. I could measure the thickness, by the way, so maybe that will give me some idea. Let's do again a bounding box. So the Z is 0.04, 0.04. So it means that if I want 4 elements, let's say in the thickness, I should be around 0.001 as the maximum mesh value. So let's clear the mesh, change the hyperpaths, and let's try if this works. 0.01, and I'll keep this for this. This is second order again. Let's compute and see what I get. So I just saw I have around 200,000 elements, which might be a bit small. So I'm just guessing because I had some tries and, actually Code Aster and Salome Meca, it has some kind of limitation in terms of model size. You cannot go like calculate like million elements model, it would just crash your computer. So maybe it's a bit too much, especially it's second order, it's too much. Let's just decrease a bit the number of elements. So clear mesh data, edit. So let's double that. Now it's 49,000 elements in total. Nodes, not elements. Sorry, you have 27,000 tetrahedrons. So I think now it's much more reasonable. This might be a bit, only two rows. Let's do it slightly smaller. I know okay, so 1.5. Let's try 1.5. Okay, now I have around 100,000 elements and 57,000. And now I have 3 layers of elements here. I think I'll use this one. That's better. And okay, now I need to regenerate the mesh groups. So because I still have my geometry mesh groups, it will be pretty straightforward. So I'll go into mesh, create the groups on geometry, select my mesh, click on the small arrow here, select my geometry, okay, and not sure what happened, but I don't see my mesh groups. I think I did something, I don't know. Groups, let's try again. Geometry, apply. Okay, now it appeared. I don't know what I did. Maybe I just closed it. Okay, let's view that. Always view your mesh groups to be sure that this is correct stuff that you're looking at. And it's fine, pretty fine. Okay. And now I would say I don't have much more to do. I just need to go back to the Code Aster module, make sure your model is loaded again. So you don't see it anymore here. It has disappeared, and that's because you basically changed the mesh set. So what you have to do is just double click on the read a mesh to reread your mesh, and you see the name hasn't changed, it's still the same, so your model will automatically be loaded again, and it should be fine. I can directly go to history view and just click on current case and run that again. And now just pray that it becomes green from the first time. So it takes a bit more time because the model is larger. As seems it will be nearly done. Yeah, green. Great. Wonderful. Now let's have a look at the results. So same stuff, going to case view, data file, and let's reopen my model. And here it is. So hide the previous models that I had, and let's have a look only at this one. So we can have a look at the mesh to be sure that this is the right mesh, which is fine. Let's add my filter. First, before adding the filter, let's generate the vectors. Then let's add my mechanics Alno field to surface filter. Apply. And let's add my warp by vector filter. So you see I activated this option, so it's automatically apply and don't have to click on apply every time, which is cool. And now I can have a look at the results. So this is the displacement. By the way, I can compare with my previous model, because let's compare. Let's compare with my previous model. Yeah, you see it was exactly the same. So not so much increase in accuracy. I'm really getting the same results in terms of displacement, but in terms of stresses, oh, is it the same model? Wait. Maybe I'm telling you. No, it's different mesh set. You see, mesh is different. Let's have a look at this one here. It's different mesh. It still surprises me that the displacement's maximum value is still the same. But anyway, looks like it's the same. Oh, what did I do? Okay. Oh, I think I just closed Paradise. Shit. Oh no, okay, I switched the scene. Okay. Okay, let's have a look at my form with a stress, which is here. And this time, the mesh distribution looks better. Let's change slightly the colors. For that, let's have a view. Windows color map editor. Where is it? It's hidden somewhere. It doesn't want me to change the colors. Ah, okay. Let's take that out. Can put it on this side. It's easier to view like this. Let's decrease the number of color to 12. Maybe I like it like this. And what you see, if you look at the colors like that, especially if you have few colors, you're better able to see where higher stresses are concentrated. And we can see here that in this case, I have this small region here, which, I'm wondering why I have this kind of discontinuity in between. Why do I have this kind of singularity here? And this is probably just due to the fact that I fixed those surfaces, and there is just a discontinuity of the degrees of freedom in between which generate this kind of singularity. So I cannot really trust those results here as being the maximum von Mises stress in this model. This is probably just some kind of artifact. And the best way to, let's say, so how do you know what is the real stresses, what is the not the real stresses? But I will just tell you that you should ignore the stress here. But how do you know how much stress you have in the other areas because this is here, right? It's already giving you the maximum here. But let me show you a quick method that I have found out to kind of rescale this in the right, let's say, right mesh, right size, so I get a clear understanding of what is the real maximum stress. So the way I found is to select some cells. So there are some very small buttons here. You can use to select some cells. This will only select some cells at the top. So you can also select at the bottom like this. And then I'll just zoom on this part where I have all the stresses. I have to reselect it like this. That. So even if I don't have all the elements selected, it's okay. Just to give me, you'll see, just to give me an idea of the range of the legend. And I'll just remove this from the selection. So to remove this, I'll again here, and there is a remove substrate selection shift. So just unselect this stresses here in this area. I just unselect it like that, and I'll do the same on the other side. Okay, so now that I have a certain number of elements selected, I'll use a filter called extract. So warp by vector extract selection. And you see that this will give me a model where basically I don't have those high stresses zone. And what I want to do here is simply to resize the legend to the data. So there's this button here, rescale to data range. And now I have an idea of the real maximum stress, which is actually located in this region here, which is around 2.1 MPa, or sorry, 215 MPa. And now I can just hide this and come back to the previous and select this, and I'm keeping this scaling. So sorry, I didn't keep the scale actually. So the scale of the legend was, so you can set like rescale to custom data range, rescale all time step maybe. So 2.1 E8. So this is supposed to reset the legend to, yeah, and now it works, it reset the same value. And now this part here is much more red, but I don't care about because this is fake stress actually. It's not real stress. This part here is probably more interesting to me. And now I have much better understanding of how to read and how to understand those results. Okay, and that's all for this video. I hope that this was very useful. I tried to go in all details today. So if you like it, please like the video, please post the comments, let me know. And again, thank you very much to watch my channels, watch my blog, and all the things I do. Thank you so much.